So in this section, we're going to consider what's called ambipolar transport. And in the general equations that describe the dynamics of excess electrons in holes, it turns out that the equations are coupled, and that also the flow of excess carriers should be coupled because of internal electric fields that might exist. So for example, if we generate some electrons and holes in the same place, but then we shift them relative to each other a little bit. So let's move one of these electrons over here. There will be a restoring force. The hole will exert a pull on that electron to try to pull it back to where it came from originally. And so the excess carrier densities tend to try to stick together. And actually, this can be sort of recast in the idea of charge neutrality. So the excess carrier densities, because they're both mobile, could in general spread out and imbalance the semiconductor. You could have a buildup of negative charge here and a buildup of positive charge here. But that's energetically unfavorable. And from a force standpoint, remember that there's this Coulomb force that exists between them. So to maintain this charge neutrality, we can say that delta n as a function of x might maintain approximately the same shape as delta p as a function of x. And now let's go a little bit further and say, imagine that we generate some electrons and holes, but we're going to generate them at the same rate because we're generating them by photons, for example. And similarly, the recombination will happen by pairs of electrons and holes, so that Rn equals Rp. Equals the overall recombination rate, and then further we can write this as delta n over tau by using this relation. So let's go back to our big general equations and make some substitutions. Now, we're not sure exactly what to do with these. Let's add them together and see if something good happens. So some of the troublesome terms are these ones here, where you have the movement of charges due to a gradient in the electric field. So if we multiply this equation by mu n times n and multiply this whole equation by mu p times p, and then add them together, we can get a much simpler form where we define a so-called ambipolar diffusion coefficient, d squared dx squared of delta n, an ambipolar mobility, and if we write the equation in this form, we get an overall equation for the drift and diffusion, recombination and generation of both carrier types. For example, if you shined a laser for just a brief instant on a bar of semiconductor and you generated some electron-hole pairs only within this little slice, the movement of these electrons and holes would be coupled, and they would move together and diffuse and drift. If you put on a voltage, they'll diffuse and drift and then decay with time by this term. So putting together these equations yields these effective quantities. The d prime is dn dp, and they actually include the carrier densities inside them. So they're not pure, they're not the same pure diffusion coefficients that we're used to from our majority carrier transport. They will end up with the same units of centimeters squared per second because of this cancellation, however. And the mobility kind of similarly is weighted by the total carrier density, but it's a difference instead of a sum. And this is centimeters squared per volt second. So this master equation here governs the ambipolar transport of excess electrons and holes inside the semiconductor. So now that we've derived this ambipolar governing equation for the dynamics of our excess carriers, let's look at the most common case that we'll encounter. So the most common case that we'll use is under low injection. So we have that the excess carriers are less than the doped carriers, the doped-in carriers. And in the case of extrinsic doping, meaning we have more dopants than intrinsic carriers. So under those conditions, we can plug some assumptions into the equations, for example, for the mu prime and d prime. And it turns out that the mu prime will revert to the mu n for the minority carriers. And I'll leave it as an example for you to prove this to yourself. And similarly, the d prime reverts to the minority carrier value. So under these conditions, we can have a much simpler equation, which looks just like the equation that we've written for the majority carriers previously when we were talking about the transport for a doped semiconductor. So under these conditions of a doped semiconductor and low injection, we actually recover an uncoupled equation that governs the overall dynamics of the excess minority carriers. And so as long as we can satisfy these assumptions, we have a much simpler time of figuring out what the excess electrons and holes will do in a material. And in fact, it allows us to only consider the minority carriers in the material and not the majority carriers when we're talking about the minority carrier behavior. What that means is that these equations have been uncoupled and made much simpler with these assumptions. So this is the equation that we'll use for figuring out how most of the devices in most of the regimes of behavior will work throughout the rest of this course.